The Asteroid Terrestrial Impact Last Alert System, or ATLAS, is our planet's robotic guardian. 4 telescopes, scattered from the volcanic slopes of Hawaii to the high deserts of Chile and South Africa, scan the entire night sky multiple times, every single night. Their mission is simple: find any asteroid or comet on a collision course with Earth before it finds us. The system's artificial intelligence sifts through 100 gigabytes of data nightly, looking for tiny points of light that move against the fixed background of the stars. On July 1, 2025, the AI flagged an object, but it wasn't a threat to Earth. It was moving too fast, far too fast. It was a visitor from another star system, and it would soon raise fundamental questions about what is natural and what is not. The object, designated 3I/Atlas, appeared in our solar system like a missile. Its velocity was measured at 137,000 miles per hour, a speed so high it can only be achieved by an object that is not gravitationally bound to our sun. It is on a one-way trip, destined to approach our star once and then disappear back into the interstellar darkness forever. This alone makes it a rare and valuable target for study. But it was the object's other characteristics that began to set off alarms in the astronomical community. Its size was the first statistical shock. At an estimated 7 miles wide, this interstellar wanderer is a giant. To put that in perspective, the first interstellar object ever detected, Oumuamua, was thought to be a few hundred meters long, like a skyscraper tipped on its side. The second, the comet Borisov, had a nucleus perhaps a kilometer across. If Oumuamua was a single grain of rice, 3I/Atlas would be a bowling ball. The difference is so profound that our models of planetary formation predict that for every object this large ejected from a star system, there should be millions, if not tens of millions, of smaller ones. We should have found a fleet of smaller visitors before ever seeing one this massive. Yet here it is, only the third confirmed visitor of its kind. The speed tells an even more dramatic story. Astronomers measure an object's trajectory using a value called eccentricity. An object in a perfect circular orbit has an eccentricity of 0. Planets in our solar system have eccentricities slightly greater than 0, meaning they follow elliptical paths. Objects that are just barely unbound from the sun, like a comet falling in from the farthest reaches of our own system, have an eccentricity of 1. The trajectory of 3I/Atlas has an eccentricity of 6.141. This number is the mathematical signature of a violent past. This is what scientists call hyperbolic excess velocity. It is the speed an object has left over after it has completely escaped the gravitational pull of its parent star. Think of it as throwing a baseball so hard that it not only escapes Earth's gravity but continues flying out of the solar system without slowing down. That leftover speed is a fingerprint, a clue to the immense force that launched it. Something catastrophic must have happened in its home system billions of years ago to fling a mountain-sized object into the void with such energy. Computer simulations offer a few possible, though violent, scenarios. One involves a chaotic cosmic dance between giant planets. Imagine a solar system, much like our own, where massive planets the size of Jupiter or larger begin to migrate, their orbits shifting over millions of years. This gravitational disturbance would create chaos in the outer regions, where comets and asteroids reside. In this cosmic game of billiards, smaller bodies are flung about like marbles. Most are sent crashing into their planets or their star. But on rare occasions, the geometry aligns perfectly for a gravitational slingshot, accelerating a smaller body to escape velocity and beyond. Another possibility involves a binary star system, where 2 suns orbit a common center of gravity. As one of these stars ages, it might swell into a red giant, its expanding outer atmosphere disrupting the delicate gravitational balance of the system. The pressure waves and intense radiation from the dying star could act like a blast wave, launching objects in the system's outer debris disk into interstellar space with tremendous force. The velocity of 3I/Atlas is consistent with such a dramatic ejection event. Even more extreme scenarios involve a close encounter between 2 separate star systems. Our galaxy contains over 400 billion stars, all orbiting the galactic center. Occasionally, 2 systems will pass close enough for their gravitational fields to interact. During such an encounter, the outer comet clouds of both systems can be disrupted, with some objects being torn free and ejected at high speeds, becoming cosmic refugees sent wandering through the galaxy. The speed of 3I/Atlas, also tells a story about time. To travel from even a nearby star system would take millions of years. But the mathematics of its trajectory, when traced backward, suggests a much longer journey. The object did not come from a nearby star. It appears to have originated from a region of our galaxy known as the galactic thick disk, a population of ancient stars formed when the Milky Way was much younger and more chaotic, perhaps as long as 10 billion years ago. This implies 3I/Atlas has been traveling through interstellar space for potentially 7 to 14 billion years. To appreciate this timescale, our own solar system is only 4.6 billion years old. This object may have been ejected from its home system before the Earth had even formed, when the universe was less than half its current age. It has survived a journey through an environment far harsher than the relatively sheltered confines of a solar system. Interstellar space is not empty. It is filled with cosmic rays, high-energy particles accelerated by supernova explosions and other violent events. These particles bombard any object traveling between the stars, penetrating its surface and altering its chemistry. Over billions of years, this constant radiation bath can destroy smaller objects entirely. The immense size of 3I/Atlas allowed it to survive this journey. Its bulk protected its interior, which may have remained frozen and unchanged, a pristine time capsule from an ancient star system. The discovery itself was an event of astronomical serendipity. The ATLAS telescopes had to catch a faint dot of light moving just fast enough to register as motion between photographs taken minutes apart, but not so fast that it appeared as a streak. The object's high velocity meant the detection window was measured in days, not the months or years typical for a new comet discovery within our own solar system. Miss that narrow window, and it would vanish back into the darkness, never to be seen again. The artificial intelligence systems that patrol the Atlas data had to distinguish this one significant dot from thousands of false positives generated every night. Cosmic rays striking the telescope's sensors create bright spots that can mimic a moving object. The streaks of satellites and space debris confuse detection algorithms. The AI, trained on years of sky survey data, had learned to recognize the subtle signature of a genuine astronomical object. 3I/Atlas appeared as a point source, moving at a consistent velocity, following a path dictated by gravity, not random noise. Once the AI flagged the object, an international alert network was activated. The Minor Planet Center in Cambridge, Massachusetts, which serves as the global clearinghouse for these discoveries, verified the initial observations and calculated a preliminary orbit. Within hours, observatories across the globe from Chile to Arizona swung their instruments toward this cosmic intruder. The follow-up observations confirmed its interstellar origin and revealed something even stranger than its size or speed. It was the object's path through our solar system. When an interstellar object approaches, it can come from any direction in the sky. Imagine our solar system at the center of a giant sphere. A random visitor should have an equal chance of arriving from any point on that sphere's surface. Our planets, however, all orbit the Sun in a relatively flat plane, an imaginary disk called the ecliptic. The probability of a random interstellar visitor arriving on a path that is nearly perfectly aligned with this flat disk is incredibly small. Most comets from our own outer solar system arrive at steep angles, plunging down toward the Sun from high above the ecliptic or rising up from below it. The orbit of 3I/Atlas, however, is inclined at just 5 degrees from the ecliptic plane. It is flying almost perfectly flat, within the same disk occupied by Earth, Mars, and Jupiter. The probability of this happening by random chance is less than 0.2%. It is a statistical impossibility that made professional astronomers take notice. It was the first sign that this object was not just unusual, but anomalous. But the real surprises were only beginning. As the world's most powerful telescopes began to analyze the light reflecting from this ancient traveler. When the first spectroscopic measurements arrived, astronomers found themselves looking at data that violated the basic rules of comet chemistry. Every comet previously studied, whether from our own solar system or the interstellar comet Borisov, is a mixture of ice and rock. When these objects approach the Sun, the ice turns directly into gas, a process called sublimation. The primary ingredient is always water ice. 3I/Atlas shattered this pattern. Its chemical fingerprint showed that it was releasing enormous quantities of carbon dioxide gas, while showing very little water vapor. The James Webb Space Telescope measured the output directly, finding that 3I/Atlas was expelling 129 kilograms of carbon dioxide every single second. This is a production rate comparable to a small industrial factory on Earth. This gas creates an invisible cloud, or coma, around the nucleus that extends over 200,000 meters. The ratio of carbon dioxide to water was measured at 8:1. This is the most extreme imbalance ever recorded in any comet. Typical comets in our solar system show the exact opposite, with water dominating carbon dioxide by a factor of 10:1 or more. 3I/Atlas inverts this relationship so completely that it suggests it formed in a place where the fundamental building blocks of planets were radically different from our own. Spectroscopic analysis works by spreading the light from an object into a rainbow of its component colors. Within this spectrum, dark or bright lines appear at specific wavelengths. These lines correspond to specific atoms and molecules, each of which absorbs or emits light at a characteristic frequency. It is a chemical barcode that allows astronomers to identify materials across trillions of miles of space. The spectrum of 3I/Atlas showed lines for carbon dioxide that were so intense they overwhelmed almost everything else. To explain this, planetary scientists began proposing exotic formation scenarios. Perhaps 3I/Atlas formed in a stellar system where carbon dioxide ice was simply more abundant than water ice. This could happen around stars with a different chemical composition, or metallicity, than our Sun, creating a protoplanetary disk with inverted chemical gradients. Or perhaps, over its billion-year journey, a thick outer shell of carbon dioxide ice formed on its surface, trapping the water ice deeper inside where the Sun's warmth cannot yet reach it effectively. The chemical anomalies extended beyond the dominance of carbon dioxide. The object also shows evidence of complex organic molecules, but in ratios different from any comet we have ever studied. It appears to contain cyanide compounds, revealed by characteristic emission lines in the ultraviolet spectrum. These are molecules that hint at a formation environment with a very different kind of chemistry than the one that produced our solar system. But hidden within this chemical factory was a mystery that seemed to defy the laws of nature itself. Using the Very Large Telescope in Chile, one of the most powerful observatories on Earth, astronomers detected the faint signature of metallic nickel vapor being released from the object. This in itself is not impossible. Comets can contain metallic minerals that are released as dust grains and then vaporized by solar radiation. The extraordinary finding was what was missing. There was no trace of iron. Throughout the known universe, nickel and iron are cosmic twins. They are forged together in the hearts of dying stars through similar nuclear processes, and are distributed through space in predictable ratios. They have similar chemical properties and condense into solids under similar conditions. On Earth, in meteorites, and on other planets, you never find one without the other. Finding pure nickel vapor without any accompanying iron vapor is, from a natural standpoint, physically impossible. Separating nickel from iron on Earth requires advanced industrial processes. It involves high-temperature smelting, complex electrochemical processing, or other specialized metallurgical techniques. These are energy-intensive technologies designed to isolate one element from the other for industrial applications. To find this chemical signature in a comet, an object thought to be a pristine remnant of planetary formation, is profoundly strange. The mystery deepened as astronomers continued to monitor the object. Between July and August of 2025, the intensity of the nickel emission lines increased by a factor of 25. This was not a random fluctuation. It followed a steep, smooth mathematical progression, suggesting a systematic change was occurring on the object. This type of organized behavior is more reminiscent of a controlled process than the chaotic outgassing of a typical comet nucleus. This series of anomalies, the impossible size, the statistically improbable orbit, the inverted chemistry, and the unnatural metallic signature, led some scientists to consider an extraordinary hypothesis. The speculation, which began in professional circles, soon reached public attention. Space agencies found themselves in the unusual position of having to publicly address growing theories that 3I/ATS might not be a natural object at all, but a piece of artificial technology from another civilization. The conversation was amplified by analyses from prominent physicists, including Avi Loeb of Harvard University, who had previously proposed that Fuma might also have been artificial. He noted that while any one of the anomalies associated with 3I/ATLS could potentially be explained away by some exotic natural phenomenon, the combination of so many independent statistical improbabilities in a single object required serious consideration of all possibilities. He argued that the collection of evidence pointed toward a systematic origin rather than a random natural one. The rapid spread of these ideas through online communities prompted official responses from NASA and the European Space Agency. In comprehensive public statements, the agencies outlined the natural phenomena that could, in theory, account for the object's unusual characteristics. They emphasized that our understanding of interstellar objects is still in its infancy, and that we should expect to find visitors that challenge our solar system-based expectations. Regarding the nickel without iron signature, agency scientists explained that unknown selective sublimation processes could be at play. Perhaps, they suggested, 3I/Atlas contains rare nickel-rich mineral phases that turn to gas at a lower temperature than the more common iron-bearing minerals. Under this scenario, solar heating would preferentially release nickel vapor while leaving the iron locked in solid form within the nucleus. However, they acknowledged that no known mineral behaves in such a way. The space agencies also addressed the statistical improbabilities of the object's orbit and discovery timing. They pointed to the strong influence of detection bias. Our surveys are most sensitive to large, bright objects that happen to pass through the ecliptic plane, where our telescopes are most often looking. It is possible, they argued, that these apparent statistical anomalies are simply a reflection of the limitations of our current detection capabilities. Professional astronomers stressed the importance of the scientific method. The process requires that all conventional hypotheses be tested and ruled out before more speculative alternatives are considered. Even when faced with genuinely anomalous observations, the burden of proof remains on the extraordinary claim. Multiple research groups confirmed that in many ways, 3I/Atlas behaves like a normal comet. It has developed a coma and is emitting dust, consistent with the solar heating of a body made of ice and rock. Radio telescopes, including those used by the Search for Extraterrestrial Intelligence Institute, have been monitoring the object but have detected no artificial signals beyond natural thermal radiation and reflected sunlight. The emerging scientific consensus is that 3I/Atlas represents an extremely unusual but ultimately natural interstellar comet. Its strange properties are thought to be a reflection of the vast diversity of planetary formation environments throughout the galaxy. It is a messenger from a star system that formed under very different conditions than our own. Yet, as the object continues its journey inward, it is heading for a dramatic climax that will be both spectacular and, for observers on Earth, tragically hidden. On October 30th, 2025, 3I/Atlas will reach perihelion, its closest approach to our Sun. At that moment, it will be 1.36 astronomical units from our star, a distance that places it between the orbits of Earth and Mars. This is closer than any previous interstellar visitor has come during the era of modern observation. The solar heating will be at its most intense, and the object's activity will be at its peak. It is the moment every astronomer has been waiting for, and no one on Earth will see it. The timing of the perihelion creates a cosmic alignment of profound misfortune. During late October, from Earth's perspective, 3I/ATLS will be positioned directly behind the Sun. This event, known as a solar conjunction, means the brilliant glare of our own star will completely overwhelm the faint light from the distant object. Even the most powerful telescopes on the planet will be blinded. Humanity will miss the most dramatic phase of this visitor's billion-year journey. Computer models predict that the transformations during perihelion could be spectacular. The intense solar heating is expected to increase the carbon dioxide production rates several times over. Surface temperatures could rise high enough to begin sublimating water ice that might be buried beneath the carbon dioxide-rich outer layers. This sudden release of new gases could trigger explosive outgassing events or even cause structural changes in the nucleus itself. Comet nuclei have been known to fragment or break apart during close solar passages when the internal pressure from vaporizing gases overcomes the object's own gravity. The development of the comet's tail during perihelion is the most visually dramatic event that will remain hidden from us. As the object nears the Sun, solar radiation pressure and the solar wind will push the gas and dust away from the nucleus, creating a tail that could stretch for millions of kilometers. The object's retrograde, or backward, orbit might produce unusual tail structures and orientations, different from the comets we are used to seeing. Fortunately, while Earth is blinded, humanity has other eyes in the solar system. Spacecraft currently orbiting Mars will have a front row seat. The Mars Reconnaissance Orbiter, Europe's Mars Express, and the ExoMars Trace Gas Orbiter are all in a perfect position to observe 3I/Atlas during its October close approach. From their vantage point, they will achieve viewing angles impossible from Earth, providing resolution potentially 3 times better than the Hubble Space Telescope. On October 3rd, Mars will be just 47 million kilometers from the interstellar visitor, offering an unprecedented opportunity for high-resolution imaging and spectroscopic analysis. The High-Resolution Imaging Science Experiment camera on the Mars Reconnaissance Orbiter, which can resolve features smaller than a meter on the Martian surface, could potentially detect structural details on the comet's nucleus. The spectrometers on the other orbiters, designed to analyze atmospheric chemistry, will be able to detect trace amounts of different molecules in the comet's coma, revealing minor chemical species that are below the detection threshold for Earth-based observatories. By combining images from the different orbiters, scientists can create stereoscopic, three-dimensional maps of the gas and dust cloud, revealing its internal structure. These observations from Mars will document the peak activity of an object that is more than just a comet. It is a pristine sample of materials from an era of cosmic history known as cosmic noon. This was a period approximately 2 to 3 billion years after the Big Bang, when star formation across the universe was at its absolute peak. Galaxies were forming stars at rates 10 times higher than they do today, and the cosmos was undergoing its most dramatic period of chemical evolution. During this epoch, the first generations of massive stars ended their lives in supernova explosions, seeding the universe with the first heavy elements like carbon, oxygen, and iron. The age of 3I/Atlas places its formation squarely within this dynamic era. The chemical signatures locked inside it are a direct sample of the materials that were available for building planets when the universe was young. It is a fossil, not of life but of the chemical conditions at the dawn of planetary formation. The object's origin in the galactic thick disk further supports this ancient timeline. The thick disk is a fossil record of our galaxy's own violent youth. The stars in this region have a lower abundance of heavy elements compared to our Sun, which resides in the younger, more chemically enriched thin disk. The chemical composition of 3I/Atlas, with its unusual elemental ratios, is consistent with formation in this ancient metal-poor environment. It is a relic from a time when the rules of planetary formation may have been very different. And that is perhaps the most profound implication of this interstellar visitor. 3I/Atlas challenges the standard model of how planets form. That model, based on our own solar system, assumes that water ice is the dominant volatile material in the outer regions of a protoplanetary disk. This object, with its extreme 8:1 carbon dioxide to water ratio, suggests that this is not a universal rule. It implies that planetary systems can form in environments where carbon dioxide ice is more abundant than water ice. This chemical diversity suggests that the architecture of planetary systems throughout the galaxy could be far more varied than we have imagined. Our solar system may not be typical, but rather a cosmic anomaly. If 3I/Atlas represents a more common type of building material, then billions of planetary systems in our galaxy might have formed with chemical compositions completely different from our own. This opens up the possibility that planets with habitable conditions could be based on a different chemistry, with atmospheres and surface conditions unlike anything we find in our solar system. The discovery of 3I/Atlas, an object that according to our models should not exist, has transformed a field of study. In the coming years, new observatories like the Vera C. Rubin Observatory will turn the detection of interstellar objects from a rare accident into a routine survey. This facility is projected to discover dozens of new interstellar visitors every year. We will soon have a catalog of these messengers, allowing us to study their population, map their origins, and understand the full diversity of planetary ingredients across the galaxy. Each new discovery will provide another data point, another piece of the puzzle. They will tell us if 3I/Atlas is a 1 in a billion freak of nature, or if it is a typical example of the building blocks that populate the space between the stars. The chemical mysteries it carries, from its deadly cyanide compounds to its impossible metallic signature, may eventually be explained by new models of astrophysics and planetary science. But for now, 3I/Atlas remains an object of profound mystery. It is a ghost from the deep past of our galaxy, carrying revolutionary evidence that our understanding of cosmic chemistry and planetary formation is incomplete. As it continues its eternal journey, heading back into the void from which it came, it leaves behind a transformed scientific landscape and a question that will drive the next generation of discovery. What else is wandering in the darkness between the stars?